Hi guys, so in continuation of our lecture on SVM, today what we will see, as I have mentioned in my last lecture, so this transformation, data transformation to make it the non-linear separable data which cannot be separate, which are not separable linearly. So there is non-linear data. We have we try to use linear SVM for that. For that, what we have done, we try to use the so that we can use the linear SVM for this non-linear separable data. We have transformed the data from non-linear data to linear data. For that, what we have used, when transformation, the transformation was in a input space of say x, and that transformation we have changed it to a different input space of a higher dimensional. So when we have changed it to higher dimensional, the computational increases. Computational, when we try to compute the optimization constraint problem, there also computational increases. When we try to find out the different parameters values, there also the computational. When we do the dot product w dot x or xi dot x, so this dot product basically we do if it is in an n dimensional space, so it is n multiplication plus n addition. So similar, when the dimensional increases, the computational increases. So now how to solve that, how to address that? So there are two concepts. One is the dual formulation of optimization problem, and another is that we will introduce a new very intelligent method which is called kernel trick. So as we have discussed, what is the different issues? First, of course, there were one issue I forgot to mention. That one issue was also mapping. How will I map? What mapping procedure I will use? As I have shown you, if whether I will use, suppose the dimension is in R2, so in dimension of R2, whether I will keep it in R2 only, or I will use I will transform it to R3, or I will transform it to R4. Basically, how many attributes do I need to use? So based on the number of monomials, so how each monomials I will be mapping it to an attribute of the higher dimensional. So that is this mapping. Which mapping exactly? There is no hard and fast rule that I'll have to use this mapping. So since there is no such hard and fast rule, how I will do the mapping? That is one of the issue. Then definitely cost of the issue, cost of the mapping, dimensionality problem, and computational cost. So these are some of the issues. So mathematicians have cleverly proposed an elegant solutions to the above problem. So that is the dual formulation of optimization problem and kernel trick. So let's see what is that. First we will see dual formulation of optimization problem. So we have already learned the Lagrangian formulation to find a maximum margin hyperplane, isn't it? So we have formulated our problem as a maximization problem. Earlier it was a minimization problem 2 by w, and which we have changed it to w by 2, and we found it we have formulated it as a maximization problem. So we have learned a Lagrangian formulation to find a maximum margin hyperplane of a linear SVM classifier. Such formulation, what we have seen, such formulation is called the primal form of constraint optimization problem. The formulation what we have done till now, this is also called the primal form of the constraint optimization problem. Okay, so primal form of the Lagrangian optimization problem, this was my primal form. I have to minimize this w square by 2, isn't it, subject to this, isn't it? My difference between the two, what was that, my difference between two vector, I have to maximize this, isn't it? So what was this? That is 2 by w. So I had to maximize this, the difference. So this I have formulated as a minimization problem. How did I formulate it as a minimization problem? I have used this, isn't it? So I have to minimize this subject to yi w dot xi plus b greater or equals to 1. So this was my Lagrangian form. This formulation, minimize this subject to this. This I have written in a Lagrangian form as this. Earlier I have not used the term p. I have just written L is equals to this. This was my Lagrangian form. Remember, we have done this. Now I am calling this thing actually. This basically that time we did not mention specifically. This is called the primal form. Okay, this is the primal form. So a subscript, we can use a subscript P to distinguish that this is a primal form. Why we are distinguishing? Because there is some other form also, that is the dual form. Now what we will see, what is the dual form. Okay. Now here what is the lambda? Lambda is a dummy variable, it is also called Lagrangian multiplier. Okay. So LP is called the primal form of Lagrangian optimization problem. So now from this is the primal form. Now from this we will have to find out the dual form. Why we will find out the dual form? We will see that. The dual form, to find out the dual form, what we have done first, as we have seen, to minimize this Lagrangian, what we have done del L by del W, del L by del B, so that from that we have found different expression, isn't it? So here del of LP by del W, we found this, W is equals to this, isn't it? Isn't it? Because what was this? W minus this, we got 0, so W is equals to this. That is what we have done earlier. You can refer to previous lectures, and this also, when we have done del L by del B, we got this, summation of lambda I yi is equals to 0. Now what I will do is that in my primal form Lagrangian, I will be substituting this W value, and I will be basically I will be substituting this value and this value. Okay, in my, I will substitute this in my primal Lagrangian form. So this was my primal Lagrangian form. Fine. So I have done first order differentiation with respect to W, and I got this. Then I have done first order differentiation with respect to B, and I got this. Okay, this too I will be using in this expression, and there is actually a big one-page calculation. So I did not show it in this slide. So this, once we substitute this and once we will be using this in this expression, we will get something of this form, where there is no B, no W, all in terms of lambda, y and x, where y is the class and x is my observation. Okay. So when I use these two equations, this one, this equation and this equation in this equation, after lots of calculation, as I told you, it is a big one-page calculation, then you will be finding this. So in short, I can write it this way, and this I am calling it a dual form, dual Lagrangian form, because primal Lagrangian, that was my Lagrangian form, and in that Lagrangian form, what I have done some sort of substitution. I did not do anything else, I have done just some sort of substitution. What I have substituted, I have differentiated with respect to W, I have differentiated with respect to B, and whatever I got, that I have substituted in primal form, and I got a different expression which I am calling it the dual form of Lagrangian. So this is my dual form of Lagrangian. So in my dual form of Lagrangian, I don't have W term, I don't have B term, and this is my quadratic term is minus here. Here my quadratic term is, this is my quadratic term, isn't it? This will give me a quadratic term. This is minus here. So the key difference between the primal LP and the dual LP forms of the Lagrangian optimization problems are given here. So there are different differences. There are many differences between the LP and LD. So what are the differences? Let's see. So LP involves a large number of parameters. Obviously, our LP has large number, it has W, it has B, it is lambda I. On the other hand, LD involves only Li, that is the Lagrangian multiplier. LP is the minimization problem, as the quadratic term is positive. LP, when we use LP, there is a minimization problem because there the quadratic term is positive, but however in LD our quadratic term is negative. I have already mentioned that, hence it turns out to be a maximization problem. So since a quadratic term is negative, then it is no longer a minimization problem, basically it turns out to be a maximization problem. So LP involves the calculation of W dot x. In LP, what we do when we find out LP, so our calculation is W dot x, dot product of W and x, but whereas in LD involves the calculation of xi dot xj. xc, we are trying to do dot product of xi and xj, two different observation data. Whereas in LP we have done dot product of W and x. If W is in n dimensional, definitely if x is in n dimensional, W is also in x dimensional. W dot x means we will have to do how we do calculate a dot product, isn't it? That you know, I don't have to tell you. So, but whereas in LD I will do the calculation of xi and xj. If I do the calculation of xi and xj, then things become easier. Why? When we try to find out a dot product of two vectors xi and xj, what we try to actually find out? You think, okay, it's there in the slide, let's see. So, there are key different, so the SVM classifier, now once we have used the Lagrangian multiplier in a primal form, earlier we have seen Lagrangian multiplier we have used, and then we have found out the different values of the parameters w, b and all, and then given any test data we have to find out it falls in which class. So, this was what we used, remember. So, del of x means which class it belongs to. So, this is how we do it, w dot x plus b. So, x is the test vector. So, if we find it a negative sign, then it falls in the class below the hyperplane. If it falls in a positive sign, it falls the class above the hyperplane. What may be the above class, what may be the below class, that accordingly what you have specified. Whereas the dual version of the classifier, so it was in primal form, this was our thing. Whereas in the dual form, we will be using this, because this is my w, isn't it? This is my w. In dual form, I will not be using this w dot x plus b, but instead I will be using this formula. Xi being the ith support vector, and assume that there are m support vectors. See the difference here in the primal form. To find out the class of a x, we have what we have done. We have found out the w value. We have found out the b value, w along with the, if it is the n dimensional, so w1 to wn we found out the value, and x definitely the x is n dimensional, then only w will also be n dimensional, right. So, accordingly we found out the different x values also, and we do the dot product of this, and then we find out the magnitude and the sign of x, so as to classify, so as to predict it falls in which class. Now, in the dual form we no longer do the dot product of w dot x, but whereas in dual form this is our expression. This is our expressions here. So, this is we have a dot product of xi dot x, where x is my test vector, what is xi are the different support vectors. We have seen this here, xi as the different, for all those support vectors lambda I is not equals to 0. For vectors which are not the support vectors, for those lambda I is equals to 0, isn't it? So, this equation becomes 0. So, here we will be only multiplying all those support vectors, all those vectors which are not which are support vectors, and with those I will do the dot product of my test vector. And if I do the dot product of this test vector, what difference it will make, we will see. So, till now we have, as I told you, for solve the different issues of the transformation using the linear SVM for the non-linear data. What are the different issues we have seen, right? So, now to solve those issues, as I mentioned, there are two ways how we will solve it. Then there is not two ways, there is a trick how we will solve this problem. The first step of is dual formulation. So, we have seen this dual formulation. Now, next is the kernel trick. Okay. Does the LP and LD are equivalent? LP and LD are equivalent, isn't it? Because already what, instead of W I am using this, the W value is this, we have already found out. So, LP and LD are just equivalent. So, it is just a different form. This is the primal form, this is the dual form. Now, we will see what is the kernel trick. So, we have already learned an idea that the training data which are not linearly separable can be transformed into a higher dimensional feature space, such that in higher dimensional transform space a hyperplane can be decided to separate the transform data and hence the original data. So, this was not linearly separable, we have transformed into the higher dimensional space. Once we have transformed into higher dimensional space, we could use a hyperplane. This is the hyperplane, we could use a hyperplane to separate this to non-linearly separable data, because now it has become linearly separable. Okay. So, clearly the data on the left of figure this is not linearly separable. So, this is not linearly separable. Yet if we mapped it into a 3D, earlier it was suppose in 2D, we have mapped it to the 3D space using phi transformation, then with the map data, it is possible to have a linear dimensional boundary, linear decision boundary, that is a hyperplane in 3D space. So, see this example. Suppose there is a set of data in 2 dimensional in R2. We have a set of data which is in 2 dimensional. Let the hyperplane in R takes this form. Okay, and this data is in the 2 dimensional. Suppose if I consider a hyperplane, because it is these are not linearly separable, it is non-linearly separable. Suppose it takes the hyperplane takes this form, quadratic form. Okay, which is this is nothing but the equation of an ellipse, or maybe you can consider this. Yeah, you can consider this sort of data. This is an ellipse, right? So, now suppose we will be doing phi transformation. Now, suppose phi is a mapping from x, that is in R2 to Z, Z1, Z2, Z3 to R3 in 3D space. How will do the mapping? So, say for this term I have used Z1, Z1 is equals to x1, Z2 is equals to say this term, okay, Z3 is equals to say this term. There are 3 nomials. So, for each 3 nomials, each nomial I have used one attribute of higher dimensional. So, say Z1 is equals to x1 square, Z2 is equals to root over 2 x1 x2, Z3 is equals to x2 square. I have used 3 different attributes for the different nomials. There were 3 nomials. Okay. So, I got this. Now, that means when I use this transformation, then this has become my equation. So, this is very much a linear equation, isn't it? This is very much a linear equation. So, that means it is a hyperplane. Earlier it was a hyperspace. So, now this is very much a hyperplane, from which we will have to find out basically the different values. Once we can find the values, we will be able to classify the test data. This is clearly a linear form in 3D space. In other words, w dot x plus b is equals to 0 in R2 has mapped into w dot z plus b dash is equals to 0 in R3. Fine. So, in 2 dimensional it was w dot x plus b is equals to 0, which we have mapped it to 3 dimensional w dot z plus b dash, use a different intercept, that is b dash is equals to 0, that is in R3. This means the data which are not linearly separable in 2D now are separable in 3D, because this is a linear plane. This plane separates the data. Earlier which was separating the data? This was separating the data. It was a hyperspace. A hyperspace was separating the data. Now, what we have transformed into a linear plane. This linear plane is now separating the data. So, now we will see the generalization of this formulation, which is the key to the kernel tree. Now, we will see what is the kernel tree. See here. So, our classifier is, earlier our classifier was w dot x plus b, isn't it? What is the classifier? To given a class x, given an observation at, it falls to which class? How do I find? W dot x plus b. We have seen here this w dot x plus b. Now, it has, our thing has become this. This is our classifier now. So, this is my classifier now. Okay, I have used the dual form of the Lagrangian. So, this is my classifier now. So, now this is my classifier in the x dimensional, whatever it is, my input dimension may be 2D, 3D or whatever it is. Now, since I am converting it to a higher dimensional, I am doing the transformation so as to convert this linear to non-linear to linear. So, this transformation I am using say z. So, now I will for me now, if I want to classify given a test data x, it falls into which class? Basically x, first I will have to convert it to z, and that means I will have to find out this z belongs to which class. So, I am telling my classifier z instead of classifier x, now I can write classifier z, isn't it, because x I will convert it to z. So, classifier z, if I convert it, this I can write it in this way, xi I have done this phi transformation, x also I have done this phi transformation. Earlier my dot product was between xi dot x, now my dot product is phi dot xi to phi dot x. Okay. So, what was my dual problem? Since it was my negative term is the quadratic term is negative, so it is maximized, we have already mentioned. So, I will have to maximize this, is not it? Once I maximize this, I will find out by maximizing this, I will be able to find out my lambda value. So, maximize this subject to this constraint, we have seen this constraint, isn't it? When we have found out this expression, then we have seen this constraint. So, essentially we will have to maximize this subject to this constraint, okay? And when we maximize this subject to this constraint, accordingly we will be able to find out the lambda value, okay? Once we found the lambda value, then we will be able to do this classification by doing this dot product. Now, to see the thing here. Now, question here is how to choose phi, the mapping function, that is x is mapped to z, so that linear SVM can be directly applied. So, a breakthrough solution to this problem comes in the form of a method known as kernel trick. How to do this mapping? That was our main issue, right? So, that is the very good solution is the kernel trick. So, now what is the kernel trick? We know that a dot product here, that I was talking of this only, I told I will discuss later. So, when we talk of dot product is what we often try to measure the similarity between two input vectors, isn't it? When we do the dot product, so actually what we want to do, we want to find out the similarity between the two vectors. So, this is also, we also call it cosine similarity, the angle between the two vectors. So, if the angle between the two vectors is 0, then we can say both the vectors are almost similar. But however, if the angle between the vectors is 90 degree, then we can say both the vectors are orthogonal, isn't it? So, for here it is written, we know that a dot product, you know, right, is what is dot product, dot products, cross product, you know all those things, isn't it? So, we know dot product is often regarded as a measure of similarity between two input vectors. We call it cosine similarity. For example, if x and y are two vectors, then we can write it in this way. So, how do we find out the angle? From this expression, we can find out the angle, isn't it? What is cos theta? Cos theta is magnitude of x into magnitude of y by x dot y. That will give me cos theta. So, theta will be cos inverse of that, what we get. So, for similarity between x and y is measured as a cosine similarity. So, if theta is equals to 0, then they are most similar, the vectors are most similar. If the theta is 90, then it is orthogonal. And as if theta is equals to 0, then cos theta is equals to 1. Then if theta is equals to 90, what will be cos theta? Cos theta will be 0. So, if the cos theta values reduces from 1 to gradually 0, our similarity reduces gradually. So, now analogously, if xi and xj are two tuples, then xi xj is regarded as a measure of similarity between xi and xj. See here, when using the classifier, what I have used, xi dot x, I have used the two dot product. Similarly, here also I have used two dot product. So, if xi and xj are two tuples, then xi dot xj is regarded as a measure of similarity between xi and xj. Fine. So, again, phi of xi and phi of xj are transform feature of xi and xj respectively. Thus, phi of xi dot phi xj is also should be regarded as a similarity measure between phi of xi and phi of xj, because if xi is a vector, definitely phi of xi is also a vector, isn't it? We have transformed it from one dimensional to another dimensional, but it is xi is also a vector, the phi of xi is also a vector. So, if xi dot xj, if we regard it as a measure of similarity, then phi of xi dot phi of xj also will be regarded as a measure of similarity in the transform space in the different dimensional. This is an important revelation and is the basic idea behind the kernel trick. Okay. Now, naturally question arises, if both measures the similarity, then what is the correlation between them? So, now xi dot xj, this dot product also measures the similarity. When we try to find out the class of a the test data, basically we try to find out this test data how much it is similar to the different support vectors. When we are doing the dot product, means essentially we try to find out this test data is how similar with the support vectors. Based on this similarity, we basically classify it to this data or the other data. So, what we have done for xi dot xj, xi dot x, basically the test data, if my test data is x, we find out the similarity measure between the support vector and the test vector. Here also it is phi of xi dot phi of xj. When we do here also we do the same similarity measure, but in a different dimensional, in a transform dimensional, isn't it? So, now what is the relation between them? Is there any correlation between xi xj and phi xi phi xj? Now, let us try to find the answer to this question through an example. So, without loss of generality, let us consider a situation stated below. We will be using the same equation which very recently we have used. So, suppose it was from R2 the input dimensional to input space, we have converted into R3. So, it was x1 is equals to z1, x2 equals to z2 to root 2 x1 x2 equal to z3, the same example which we have used. So, if my xi is this, xi1 xi2, if my observation given observation xi is xi1 xi2 and xj is this, these are any two vectors in R2. Similarly, then my phi of xi will be this and phi of xj will be this, isn't it? Nothing but the attributes. Here I have 3 attributes z1, z2, z3. So, these are the 3 attributes in my transform space. So, are the 2 transform function of xi and xj in R3. So, now let us try to find out the dot product of phi of xi and phi of xj. If I find out the dot product of phi of xi and phi of xj, now this is my one vector, this is one vector. Can't I write it in this way? I'll just, when I have to find out a dot product, so I have written it in this way. So, this is what I got. Okay. This is nothing but this is a vector, phi of xi is a vector, phi of xj is a vector. I have written it in this way and I got this. Okay. This again I can write it in this way, isn't it? This I can write it in a plus b whole square. Again this I can write it in this way. And what is this? This is nothing but xi dot xj whole square. See here, that means phi of xi dot phi of xj is xi dot xj whole square. Ignore the term whole square, whatever it is. Basically, what I found that phi on xi and phi of xj is somehow related to xi and xj. That means there is a correlation between phi of xi dot phi of xj and xi dot xj. There is some correlation. The square, cube, whatever it is, forget about that. Just that phi of xi dot xj is correlated to xi dot xj, because we have seen when we have done phi of xi dot phi of xj, ultimately we got xi dot xj square. So, with reference to the above example, just what we have seen, we can conclude that phi of xi dot phi of xj are correlated to xi dot xj. Fine. In fact, this we can, in general also we can prove that for any feature vectors and their transform feature vectors. We can take, if we take any feature vectors, any transform, this is just a simple example we have seen. For any such feature vectors and its transformed, if we see, we will be able to prove this, that there is a correlation between the transform vector as well as the original vector. And this proof, it is not possible to discuss the proof here. More specifically, there is a correlation between dot products of original data and dot products of the transformed data. Okay. So, based on this above discussion, we can write dot product of xi dot j, it implies this dot product of phi of xi dot phi of j, it implies this k. This k denotes a function which is more popularly known as kernel function. Now, what is this kernel function? What is this k? We will discuss in the next lecture. Just to give an hint, just to understand what is this kernel function, let me give you an analogy of a very non-technical analogy. Like, okay, suppose I have here two fruits, and I have asked you to compare these two fruits. So, the person whom I have asked to compare these two fruit, suppose he is not a very intelligent person. So, then what he will compare, if both the fruits are red, suppose, then this both the fruits are red, that is one similarity, means how does both the fruits are, how similar they are, if I want to find out. So, he will tell both the fruits are red in color, both the fruits are round size, both the fruits have the almost same size. So, this sort of comparison will give. But if I ask to compare to a very intelligent person, so in what way the intelligent person will compare? What she will do is that she will try to find out, okay, what are the different values of this food, what vitamin it has B vitamin, magnesium, zinc, whatever it has, and accordingly the other fruits also what it has, and how it helps the person who consumes it, how it improves the immunity of the person who consumes it. So, accordingly we will find out the similarity measure of these two fruits. That is how intelligent person will do. The other dumb person will just based on the color, shape, size will give an comparison. Now, if it is the intelligent person will do this sort of compare similarity between these two fruit. Now, likewise, suppose if consider two other fruits in a different soil. This is in Indian soil, suppose in UK soil. In UK soil, suppose we have two different fruits. So, in the similarity measures, so if we try to find out the similarity measure, suppose this, when you are comparing the two different fruits, here I have compared two fruits X and Y, there in the UK soil another two fruits A and B. So, similarity measure may be same level of vitamins content, zinc content, magnesium content, whatever it is, and how it improves the immunity level. So, if that is there is a correlation between those two fruits and these two fruit in Indian soil, then we can say these are correlated. These two, maybe these are different fruits, look wise it is maybe very different. So, but similarity wise, this is the similarity measure of these two, how it affects a human being, whoever is consuming it, and similarly these two fruits in the Indian soil, how it affects how when a person consumes it. This way we can say these two fruit, if they are similar, we can say that they are correlated. So, that is what basically is the kernel function. Now, what is K? There are many standard functions which we will which can be used as a kernel function, which and how we can use this for us in this SVM, that will be seeing it in my next lecture. So, in this lecture we learned about the dual formulation of the optimization problem, okay, from the primal form, how we have converted it to the dual form. And we have also learned an important concept, that kernel tree. We have just learned it, how it can be used, and how it helps us in solving this transformation problem, that we will be seeing in my next lecture. Okay, with that, thank you guys.